All right, so welcome to the organic chemistry unit of Chemistry 30. Today what we're going to get into is distinguishing between organic and inorganic compounds or not organic compounds. We'll get into the types of formulas that we're commonly going to be using in this course, and we're also going to get into naming as well as drawing alkanes. Okay. So in organic chemistry, which is not to be confused with inorganic chemistry, but in organic chemistry, all substances can be divided up into organic and inorganic compounds. Okay, so what we're mostly concerned about is organic compounds. So those are going to be all the compounds that contain carbon, and they often have hydrogen in the formula as well. And sometimes we get some other atoms such as oxygen, fluorine, nitrogen, sulfur, and phosphorus. But there are some exceptions to this definition of an organic compound. So sometimes you'll have compounds which have carbon in them, however, they're not considered organic. Okay, so these exceptions are going to be any compound that has polyatomic ions in them, such as carbonates. So as a reminder here from Chemistry 20, carbonate ion would be CO3 with a 2- charge. Okay, if you're wondering or thinking to yourself, it's been a minute since Chemistry 20, and you're wondering where you could find this polyatomic ion, what you can do is you could head to your Chemistry 30 data booklet, go to the periodic table, and there's a list of common polyatomic ions. So carbonate is listed right here. Okay, and all of these mentioned under ionic compounds, they're going to be able to be found in the periodic table. So hydrogen carbonates, that's just HCO3, 1-. Cyanide ions, CN, 1-. Thiocianides, that's where we have sulfur, carbon, and nitrogen with a 1- charge. And then carbides are C2 with a 2- charge. So if you see any compound with carbon, but they have either carbonates, hydrogen carbonates, cyanides, thiocianides, or carbides, they're going to be considered ionic compounds. Okay. Additionally, compounds which are oxides are not going to be considered to be organic. So that would be carbon monoxide, carbon dioxide, and carbon disulfide. Okay, so make sure you know what compounds are the exceptions to being considered organic. Okay, so just as a note, tetrachloromethane, so that's this CCl4, that's going to be considered organic. And we have dichloro-difluoromethane, that's also considered organic. We are going to get into how to name compounds such as this. So make sure you highlight that. And this is a little bit sneaky, but elemental carbon, so just carbon by itself, is not considered to be organic. Okay, so make sure you know all of the exceptions and you're able to distinguish between what is an organic compound and what is an inorganic compound. Okay, so the reason why we have a whole unit on organic compounds is because they're pretty important for living matter. So, for example, you can find organic compounds in foods, in fats, proteins, that sort of thing, DNA, RNA, fuels, oils, fabrics, pulp and paper, wood, perfumes, cosmetics. You can find organic compounds pretty much everywhere for living matter. Now, carbon is very special because it can form big long chains, which are called polymers, and they make pretty strong covalent bonds, and they can also make double and triple bonds fairly easily here. Now, the types of formulas that we're going to be using in this unit, there's a few different ones here, but we're going to be focusing mostly on the last three when we are drawing. Okay, so the first one is going to be the empirical molecular formula. So this is probably what you're used to from Science 10 or Chemistry 20. Okay, now the expanded molecular formula, they use brackets to indicate the location of branches. So for example, what's happening here, this CH3 here that's in brackets, that is a branch that is attached to this second carbon right here. That's what this notation means. Okay. But these first two, they're not super helpful in being able to show the structures of these compounds. So that's why these last three are going to be focused on when we are dealing with drawing structures of compounds here. Okay, so actually before I move on, let's just make a note. I said this out loud, I just didn't write it. That is a branch. Okay, so the main idea behind expanded molecular formula that's still kind of missing here is we're not seeing any bonds between the carbons here. But that's going to change once we get to structural formula. Okay, so this gives us a nice clear picture of all the atoms, all the locations of the bonds, and the main idea here is that every single bond is shown in a structural formula. Okay, so when I'm talking about branches, what I'm talking about is something like this. So this right here is going to be called a branch. And we'll get into this in a bit, but this right here, this is going to be called the parent chain. So the parent chain, that's just the longest continuous chain of carbons that's in a compound. Okay, and we'll get a bit more into this later in this lesson. All right. So main idea here, shows all bonds between all atoms. Okay. So something I want to look at before we move on to condensed structural formula is notice how each carbon atom forms 4 bonds. And that's really important to know, especially when we're moving into condensed structural formula and line structural formulas. So let's make a note about that. We can do that right up here. So carbon likes to have 4 bonds. So that is pretty important. All right. Now with condensed structural formula, we're seeing the carbon to carbon bond. So this bond, even though it looks like it's between this hydrogen and this carbon, it's actually between this carbon and this carbon. Okay, so with condensed structural formula, all you are seeing are the carbon to carbon bonds, but none of the carbon to hydrogen bonds are going to be shown. Okay, so we're going to see the carbon to carbon bonds. We're going to see basically any bond between carbon and any other element besides hydrogen. Okay, this method shows all the branch locations, but the nice thing about it is that it doesn't take up as much space as the structural formula. So let's make sure we highlight this, because that's important to know. With the line structural formula, each end of a straight line represents a carbon atom, and each carbon is assumed to have as many hydrogen atoms bonded to it as necessary to give it 4 bonds. So that's why it's incredibly important for you to know that carbon always likes to have 4 bonds. Okay, so with what they're saying here is at the end of each line, or just where 2 lines meet, that's where you're going to have a carbon atom. So there's a carbon atom here, 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 as well as here. Okay. And even though they don't show it, there are implied hydrogens, and there's enough so that there's 4 bonds to carbon. Okay, so this carbon has 4 implied, so this carbon has 3 implied hydrogens because we need 3 bonds to this carbon so that it has a total of 4, right? The 4th one being this bond. Okay, now this carbon has 1 implied hydrogen because it has 1, 2, 3 bonds already. So it needs 1 hydrogen to make it so that there's 4 bonds to it. This carbon, it already has 2 bonds to it, so it has 2 implied hydrogens. Okay, and both of these carbons here, they both have 3 hydrogens implied because each of these carbons have 1 bond to it, so it needs 3 implied hydrogens to make up all the bonds that it needs. Okay, so keep in mind all of these structures or formulas mentioned, they are all talking about the exact same compound. However, as you can see, the structural formula, condensed structural formula, and the line structural formula, they're a lot more useful for seeing what this compound looks like. Okay. So, important part, each carbon is assumed to have as many hydrogen atoms bonded to it as necessary to give it 4 bonds. Okay, so I called these implied hydrogens. Okay, so why would we want to draw a line structural formula? It's just because it's faster. Okay, because otherwise in chemistry, especially organic chemistry, if you're drawing out all the compounds, you're going to spend a lot of time drawing out hydrogens unless you draw line structural formulas. Okay, so with naming compounds in our unit, which is called organic chemistry, this is a very important table. Okay, so make sure to put a star by it. So each of these are root or stem names, whatever you want to call them, that are going to correlate to how many atoms of carbon that are in the specific part of the compound that you're talking about. So make sure that you highlight this. Because you're going to need to know this entire table. Okay, so the stem name meth means that you have 1 atom of carbon. So if we were talking about an alkane, which we're just about to get into, and we wanted to say that this compound only has 1 carbon in it, we would call it methane. Eth means that you have 2 carbons in the compound or in that part of the compound, so we would call it, if we're naming an alkane, ethane. Okay. 3 carbons, the stem name would be prop. For 4 carbons, bute, even though it's spelled like but, it's pronounced bute. For 5 carbons, pent. Hex for 6, hept for 7, oct for 8, non for 9, and dec for 10. Okay, so we've got the alkane name, but we also have the branch name. Now, the key thing about branches is that the suffix, when you're talking about a branch, the suffix is always YL. Okay, whereas an alkane, as you can see, the suffix is always this ANE. Okay, so that's important to note here. All right, so now we're getting into alkanes. What exactly are they? So alkanes, they are saturated aliphatic compounds. Okay, so what on earth does that mean? Okay, so saturated, that just means that the compound has as many hydrogens as possible, and you can only get that if your hydrocarbon has only single carbon-to-carbon bonds. So this word saturated, that is related to this compound only having single carbon-to-carbon bonds. If a compound has double or triple bonds in it, then it is no longer saturated, or it no longer has the most amount of hydrogens possible. All right, now let's move on to this word aliphatic. What exactly does it mean? So what it means is when you're talking about an aliphatic compound, you are referencing any compound that does not have an aromatic ring in it. Okay, what exactly is an aromatic ring? We are going to get into that in later lessons. Okay, but an aromatic ring, if you really wanted to know that right now, an aromatic ring looks something like that. Okay, so this is called benzene, and any compound that has benzene in it is going to be considered aromatic. Okay, alternatively, if you want to think of it more in relation to alkanes, if a compound has benzene or this aromatic ring in it, then it is no longer considered aliphatic. Okay, so alkanes are saturated aliphatic compounds, which means they only have single carbon-to-carbon bonds and there's no benzene rings in it. Now, the general formula for alkanes is going to be CnH2n plus 2. So what does this mean? So it means N is going to be some amount of carbon atoms in your compound. And the amount of hydrogen atoms is going to be 2 times the amount of your carbon atoms plus 2 more hydrogen atoms. Okay? So if we're looking at some examples of alkanes, we've got methane, and we've got ethane, propane. Okay, so all of these are following this formula, right? So C1H4, so this one, it's invisible right here, and you really don't have to write it. But if we look at 4 for the hydrogens, right? So the amount of hydrogens is H2n plus 2. N, or the amount of carbons, is 1. So if we plug that in, well, 2 times 1 is 2, plus 2, well, that's going to be 4. Okay? So all of these chemical formulas follow this general formula because they are alkanes. some properties of alkanes are they're nonpolar, they do not have any hydrogen bonds, and therefore, because they have no hydrogen bonds, they're not going to be soluble in water. So some alkanes that are between 1 to 4 carbons, they're typically going to be in the gas state. If they're between 5 to 16 carbons, they're typically going to be liquid state at room temperature, and anything above 16, they're going to be solid. Okay. For some uses, you can find them in everyday life, such as methane, propane, butane, octane. So notice that all of these end in ane, and that's how we know that they're alkanes. Okay. They're also good for making plastics and lubricants. All right, so let's get into the rules for naming branched alkanes. Okay, so step number 1, you're going to want to figure out what your parent chain is. As a reminder, parent chain is the longest continuous chain of carbon atoms. Okay. For step 2, we're going to number the carbon atoms of your parent chain from the end that's going to give the attached groups the lowest possible numbers. Step 3, we're going to indicate the number of the carbon atom to which each branch is attached, if you have any branches. Okay, and that's going to tell us what position that branch is at in the compound. Step 4, determine the branch types involved. So if you have a branch that only has 1 carbon in it, you're going to call it methyl. If the branch has 2 carbons, you're going to call it ethyl. Just as a reminder, that YL ending signifies that you're talking about a branch. So that's that branch suffix. Okay, if you have more than any type of branch, you need to be placing di, tri, tetra. So if you have in a compound 2 methyl branches, they could be on the same carbon or they could be on 2 different carbons. But if you have 2 methyl branches, you need to be saying dimethyl. Okay, you also need to be specifying where on the parent chain those branches are going to be located. Okay, step 5, put the branches in alphabetical order. So very key that you list your branches in alphabetical order, and the di, tri, tetra prefixes, they're going to be ignored for alphabetizing purposes. And then last but not least, we put the name together. Okay, so each branch requires a number to signify which carbon it's attached to, and the numbers are separated by dashes from the branches. Okay, so how we can just reword that last part here. So the numbers, because this is an important additional detail here. If you have more than 1 number to reference, because you have more than 1 of that type of branch, the numbers are separated by commas. Okay, and dashes separate numbers and letters. Okay, so this will make a little bit more sense once we actually get into the names, but for your alkane name, the branch always comes first and then the parent chain name comes second. And you're always going to write it as 1 word. Okay, so some examples of alkane names, that's all 1 word, would be 3-ethyl 4,7-dimethyl decane. So this part right here, that is the part that talks about the branch. How you know that is because of that YL ending. Okay, this part right here, the decane, that's talking about the parent chain. Okay, how we know is because it has that suffix ending ane, which tells us that our parent chain only has single carbon-carbon bonds. So that's how you know it is an alkane. So this is for branches, and that's the parent chain. Oh, spelt chain wrong. Okay, if we look at this other example, 3,3,4-trimethylhexane. So this part talks about the branch, or the branches, I should say. And how I know there's more than one branch is because it's saying we have, actually I'll point over here, we have 3 methyl branches, or 3 branches that only contain 1 carbon, and they're on carbon 3, 3, and 4. So 2 of them are on carbon 3 in the parent chain, and 1 of them's on 4, or carbon 4 of the parent chain. Okay, that's what that's telling you. Hexane, that's the parent chain. How do we know it's a parent chain? Well, it comes last, and also that A-N-E ending tells us that it's an alkane. Okay, so let's look at our first example here. Step 1, locate your longest continuous chain of carbons. That is your parent chain. So I'm looking here, and that looks like the longest continuous chain. Okay, so we got 1, 2, 3, 4, 5, 6 carbons there. Now, could I have done this? I could have, but let's count how many carbons there are. 1, 2, 3, 4, 5. Well, that's not the longest continuous chain. Could I have gone like this? So this has 1, 2, 3, 4, 5, 6 carbons in it. So I've kind of tied with what I originally have. So you could use this as your parent chain name. You will still get the same exact name that you will get when you use this as your parent chain. Okay. Now, last but not least, could I have used this as my parent chain? Well, how many carbons are there? 1, 2, 3, 4, 5. Well, that's not the longest continuous chain, so that means you can't use it. All right, so let's put this down as our parent chain and figure things out. Okay, so we have 6 carbons in our parent chain, and there's only single carbon-carbon bonds. So when you're looking to name stuff, this is kind of where your brain should be at. So bonds, only single. Which means we got to use the suffix ane. Okay, and actually I'm going to put a dash there. Make it easier to see that's a suffix. Okay, even if there was only 1 double bond, that would make it so that it is no longer an alkane. Okay, so if there's only single carbon-carbon bonds, that is the only case in which you will have an alkane. Now, our parent chain, that had, as we counted up, that had 6 carbons here. So let's write that out, 6 carbons. Okay, so that tells us what stem name that we should be using. Okay, so if I go back and we find, okay, 6 carbons, that means our stem name is going to be hex, to mean that this parent chain has 6 carbons in it. Okay, let's deal with the branches. So our branches are right here and here. So we have 2 branches, and in each of them, there's only 1 carbon. Now the stem name, that means only 1 carbon, that's going to be meth. And because they're branches, we're going to use that YL ending. Okay, so let's write this out. So 1 carbon in both branches. So that means we got to use the stem name meth. there are 2 1-carbon branches. So that means we got to use the di prefix. Okay, maybe I'll add a dash there to make it look more like a prefix. Okay, so do you need to write this whole process out every time you're naming a compound? No, but this is just me taking you through the process that I think about when I'm looking at a compound and I'm naming it. All right, so we've kind of boiled down some of the parts of what we need to be using for our name of our compound, okay? But we need to be able to tell people where exactly these 2 branches are on our parent chain. So we could number our carbons in our parent chain like this, from left to right. Or we could label them from right to left. That's an option. However, you always want to stick with the option that's going to give you the lower numbers on your branches. So let's look and see what we're working with. So I'm looking at the purple numbering here. The purple numbering says I have branches on carbon 2 and carbon 4, whereas the pink numbering says that I have branches on carbon 3 and 5. So I need to go with the set that gives me the lowest overall numbering, which is going to be 2 and 4. So that's why I'm using that. So where can I put this here? I'll just write this name right here. So remember, talking about the branches always comes first in a name. So I'm going to go 2, 4 to say I have branches on carbons 2 and 4 in the parent chain. A dash to separate out numbers and letters, and I need to say di because there's 2 of the same type of branch, methyl. So meth means that there's 1 carbon in each of these branches. YL is just a suffix for branches. Okay. And now I need to talk about my parent chain name. So there's 6 carbons in this parent chain. So we said, okay, make sure that we write hex as our stem. And then because there's only single carbon-carbon bonds, we're going to end it with ANE. So hexane. I'm going to move this closer to really make it obvious that this is all one word. Okay, so this right here is your answer. This is what this compound is called. All right, let's move on to the next compound. So step 1, let's identify our longest continuous chain or our parent chain. So I'm going to use this. Okay. Now, could I have instead gone like this? Yes, because this option gives me 1, 2, 3, 4, 5, 6, 7 carbons in the parent chain, and this option 1, 2, 3, 4, 5, 6, 7 also gives me 7 carbons in my parent chain. Both will give you the same end result for your name. The reason why I'm going with this is just because it's a little bit easier to see where your branches are or how your parent chain looks. Okay, so I'm circling my branches just to make it a little bit more obvious. Okay, and let's do our numbering. You either start from left and go right or right and go left. So I'm gonna go 1, 2, 3, 4, 5, 6, 7 versus 1, 2, 3, 4, 5, 6, 7. Okay, so our options are going to be, for the purple numbering, our branches are on carbons 2, 4, and 6. Or with the pink numbering, our branches are going to be on carbons 2, 4, and 6. So because numbering it either way gives you the same numbers, it really doesn't matter which way you number your carbons here because they both give you the same end result. Okay, so 2, 4, 6. Now let's look at these branches. Each of them only has 1 carbon in it, but there's 3 of them, so I'm going to say tri for 3, trimethyl. And now let's talk about our parent chain. So our parent chain has 7 carbons in it. So the stem name, that means 7 carbons, that's going to be hept. Okay, so I'm color coding this so it's a little bit easier to see where the branch name is and where the parent chain name is. Okay, so we're ending it with ANE to mean that this is an alkane. There's only single carbon-carbon bonds. Okay, and just as a reminder, we're separating the numbers that correlate to what carbon on our parent chain. We're separating those out with commas, and then we're separating numbers and letters with dashes. Okay, let's move on to the next one. So this right here, that is going to be our longest continuous chain of carbons here. Now, could I have also gone like this or like this? Yes, I could have, because each of these has 5 carbons. However, I'm going to stick with this just because it's a little easier to see where the branches are. Okay, so branches are all here. Okay, so branches, all of them have 1 carbon in them, and there's 4 of them. But we need to figure out, okay, what carbons in the parent chain are these branches on? So let's number these. So our options are going to be 2, 2, because there's 2 branches on the second carbon if we're going with the purple numbering, and 4, 4. Or if we go with the pink numbering, it's going to be 2, 2, 4, 4. So once again, we're using the same numbering. Doesn't matter if you go with pink coloring, or sorry, pink numbering or purple numbering. So 2, 2, 4, 4. And we have 4 methyl branches. So I'm going to go tetra, because that means 4, methyl. And now for our parent chain, there's 5 carbons in the parent chain. So for 5, that's going to be pent. Okay. So just as a note, most of the time for the stem names, you're going to be using 1 through 7 fairly often. 8, 9, and 10 are rare, but you still need to be aware of the stem names for those as well. So this is going to be pent for the stem name, and because there's only single carbon-carbon bonds, it's going to be ANE. Okay, and there we have it. So the reason why we have to say the carbon number twice for each of the branches is just to say there's 2 branches on carbon 2, and then there's 2 branches on carbon 4. That's why we have to say both of these numbers twice, is just so that people know exactly where all 4 of these branches are. Okay, moving on to this next one here. So if I designate this as my parent chain, we have 1, 2, 3, 4, 5 carbons in this parent chain. Okay, but let's see, if I go like this, I have 1, 2, 3, 4, 5, 6 carbons in my parent chain. So this is the longest continuous chain. That's what I go with. Okay, here's my branch. And I need to number this so that the branch has the lowest number on it. So it makes sense to start from here. 1, 2, 3, 4, 5, 6. So my branch is on carbon number 3. So 3, and there's only one branch on this carbon, so I don't need a prefix to mean that there's only one branch. I can just write 3-methyl. Okay, and now I need to talk about my parent chain. There's 6, so that's hex. There's only single carbon-carbon bond, so ANE for our ending. Okay, for the last one, we have our line diagram here. So it's helpful to know where your carbons are. So there's carbon here, 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 and at the ends of these sticks. So anytime you have the end of a stick or 2 sticks meet, you have a carbon there. Or 3 sticks meet, looking at this one, you got a carbon there. All right, so looking at this, my parent chain is going to be this one. So let's count how many carbons. We've got 1, 2, 3, 4, 5, 6 carbons there. Okay, now my branches are here. And I want to make sure when I number the carbons on my parent chain, I'm giving these branches the lowest numbers possible. So it would make sense to start counting from left and go right. Okay. All right, now looking at our branches here, we've got 2 methyl branches and we've got an ethyl branch. Remember that you need to order your branches when you're writing out the names alphabetically. So even though the ethyl branch, or the branch that has 2 carbons, doesn't come like first or left most in the structure, we still have to mention it first because we got to order our branches alphabetically. So it's on carbon 3, our ethyl branch. Eth is just a stem name that means 2 carbons. Okay. But then I want to talk about these methyl branches. So I got to separate the letters and the numbers with a dash. And I got to say, okay, my 2 methyl branches are on carbons 2 and 4. Since there's 2 of them, it's dimethyl. And then let's talk about our parent chain. Well, there's 6 carbons there. And there's only single carbon-carbon bond, so ANE. There you go. Now we're going to switch around and we're now going to go from the name to the drawing. So this first one here wants us to do a structural and a line formula. Okay, so for a structural diagram, if we go back, that's the one where we're showing every single one of the bonds. Okay, the line diagram is going to be this one where we're only drawing the bonds between all the carbons and the hydrogens are implied. Okay, so let's first do the structural one. Okay, and I like to start with the parent chain. So parent chain is propane. Prop means that there's 3 carbons here. So let's go 1, 2, 3. I'm going to worry about the hydrogens later. Okay. Now for the branches, okay, it says 2,2-dimethyl. So there's 2 branches on the second carbon. So if I number my carbons 1, 2, 3. Okay. We've got in the basic structure now. What we need to do is we just need to fill in the hydrogens. Okay, so remember, every carbon likes to have 4 bonds to it. So I'm putting 3 hydrogens here to make 4 bonds to this carbon. This carbon doesn't need any hydrogens because it already has 4 bonds. But the rest of these all need 3. Okay, and there you go. So that was the structural diagram. Now let's do the line formula of the exact same thing. So we have 1, 2, 3, and our branches be there and there. Okay, could you also draw it a little bit differently? You could have your parent chain 1, 2, 3, and then both of your branches up like this. Both of these are the same compound here. All right, so as you can see, ooh, those hydrogens went away. Let's get them back in there. As you can see, the line formulas are way faster to draw than the full structural diagram. All right, moving on. For ethyl 2,3-dimethylhexane, we want a condensed structural formula. So this is where we're only showing the bonds between all of the carbons, and we are writing in the hydrogens. So I'm starting with the parent chain. So hexane. So 1, 2, 3, 4, 5, 6. Okay, let's deal with the branches. So we have 4-ethyl 2,3-dimethyl. So 1, 2, 3, 4, 5, 6. So 4-ethyl would mean we have carbon, and I gotta move this to the side just so that everything fits. And then 2,3-dimethyl. So 2 and then 3. Now, could you put this carbon down below here? Yep, you sure could have. Okay. It really doesn't matter if the carbon for the branch goes on top of the parent chain or below the parent chain. Okay. The reason why I'm doing this is just so that it's a little bit neater. Okay, so we've got all of our carbons in. Now we just need to fill in the hydrogens. So remember, for condensed structure, you don't show the bonds between carbon and hydrogen. But once again, make sure each carbon has 4 bonds to it. Okay, so this carbon here already has 2 bonds to it, so it only needs 2 hydrogens. Okay, and I need to move this 2 over. Here we go. Okay, and there we have it. For the next one, we're asked for a line structural. So I'm going to start with parent chain because that's easiest. So octane, so there's 8. So 1, 2, 3, 4, 5, 6, 7, 8. There's my 8 carbons. The trickiest part with line diagrams is remembering to count this first carbon when you're drawing. Okay, so let's number this. 1, 2, 3, 4, 5, 6, 7, 8. So when I'm drawing compounds, oftentimes when I'm numbering, I'll just start from the left side and go to the right. But technically, if you wanted to, you could start numbering from the right and go left, like this. And so long as you follow what the name says, and for this one, put the 3-carbon branch on carbon 4 of the parent chain, you are good. So if I showed that, 1, 2, 3. So this carbon does not count for the branch. It's part of the parent chain. So that's why I was counting 1, 2, 3. How I know I have 3 carbons in my branch is because prop means 3 carbons.